Hello, I am Professor S. Sankaran in the Department of Metallurgical and Materials Engineering. Hello everyone, welcome to this NPTEL course on mechanical behavior of materials. I hope all of you would have seen the introduction video where I gave the background of this course and the prospective students who can take this course and how they can benefit. I also touched upon the broad area of this subject and its intricacies and how one would perceive about this course and what all one can learn in this course. A similar thing I shared in this introduction video. And I have also shown some demonstration, very simple demonstration, taking different type of materials, and then I applied some bending force, and then I showed some response of each class of materials. And then I just said that the purpose of this course, okay, to understand the material's response to the applied forces, right, especially external forces, right. So that is the primary objective. So I have also shared this slide there where I have given this intended audience where you can see that students pursuing BE, ME, BTech, MTech and PhD students in the branch of materials, metallurgy, mechanical, design and production engineering. Like I mentioned in the introduction video, this subject requires or rather involve, some overlapping concepts, like, though it addresses primarily the materials behavior, but the kind of, knowledge it borrows from the subjects like mechanics or strength of materials, it quite connected, okay. So if you have a mechanical background or a student who have studied the strength of materials already, you will enjoy this course. Not that others will not, but you need to put in little more effort. This is what I have been seeing in our classes also. A non-mechanical background, our students do not, possess this knowledge on mechanics or simple strength of materials knowledge. They need to put in little more of an effort to have a very smooth learning process, okay. So let me first show the syllabus. Though I have shared this information on the website, I would like to quickly review this, the content of this course. So if you look at it, what I would like to do is, before I get into the real syllabus or the subject topics, I would like to spend at least 10 to 15 hours of time on fundamentals of the general material science and what basic knowledge probably you would have acquired by this time in this subject, okay, preliminary level of ideas. I want to review all of them, and then we will recall all the concepts. We spend more time on concepts which are very difficult, that's students find it. Then we'll get into the real syllabus, okay. So my introduction and fundamentals will review the theory of elasticity and strength of material concepts. So this will take minimum, I think, at least 5-6 hours of classes we will cover, and then we will talk about mechanical testing, common states of stress in real life, tension, compression, torsion, bending and indentation. So we will be concentrating more on interpretation of the data and effect of metallurgical variables on this testing rather than our focus will be on the how to do this test and so on. So most of the aspects we will be covering about the interpretation and metallurgical parameter, how it influences the mechanical behavior and so on. Okay. And coming to this elasticity, this is again a complete overview and review we will do, which covers essentially analysis of stress, state of stress at a point, normal and shear stress components, shear stress components on an arbitrary plane, principal stresses, plane stress, plane strain, generalized Hooke's law, atomic equivalent of Hooke's law, elastic behavior of anisotropic and isotropic materials. Like I said, if any of you have already gone through strength of material, it will be a kind of redundant information for you. But I would like to cover it from the scratch because in the benefit of students will not have material students or any student do not have this background, so that they will also use this opportunity to brush up their knowledge so that it is useful. Then we'll come to plastic deformation. We will cover single and polycrystalline material deformation. Of course, I will also talk about amorphous and semicrystalline materials in details. Then strengthening mechanisms in solids. We will cover work hardening, solid solution strengthening, grain boundary strengthening, particle hardening, and high temperature deformation of amorphous and crystalline materials. And then we come to the core failure concepts like creep, mechanisms of creep of pure metals, solid solutions, metal matrix composites, creep of ceramics and polymers, and creep asymmetry and so on. And even before that, we will concentrate on fracture of solids and fracture mechanics, very important topic in an engineering design. We will spend a lot of time in this, and we will start with all basic theories, linear elastic stress field in crack bodies, crack deformation modes, singular stress field and displacement fields, stress intensity factors solutions, crack growth based on energy balance, Griffith's criterion for brittle fracture, strain energy release rate and stress intensity factor equivalence, and crack stability, R curves and J integral concepts, critical stress intensity factor fracture criterion, and then experimental determination of fracture toughness and nonlinear fracture toughening mechanisms in ceramics and other materials as well. This particular syllabus is a complete, will have a complete overlap with many engineering departments. For example, applied mechanics, aerospace, right, engineering design. All these branches will have a very elaborate study in this. I mean, the subjects they study in this field. But the focus in this course is we will connect all the metallurgical variables and microstructure based correlations will be made. So that is where you will find a difference. For that matter, the entire course content also will be offered by several other departments, or all the students, they also study this. The one primary difference in this course will be you will be always have a reference of a microstructure based or process based, or these two mechanical property microstructure correlations. That is the kind of focus in this course. So it will not be completely microstructural mechanical behavior alone. As I mentioned in the introduction video, my intention is to keep a balance between microstructure and mechanics as well as the correlation, property correlations. So all these three will have equal importance in this course. This is what I'm trying to do. Okay, let us see how we can proceed. And finally, we will cover the fatigue of engineering materials. Again, a very vast field in itself. This particular subject, again, very important in most of the core engineering departments, such as engineering design and aerospace, and mechanical, applied mechanics. Everywhere you will study. Then you will see how metallurgically we can approach this topic, and then how we can connect our subject with rest of the other approaches from the different departments. Okay, so this will be the syllabus, complete syllabus content, but I will not follow any sequence what I have just listed here. It is just to give you an idea what is the content of the whole course. I may go quite as per the fundamental how I am going to approach. Then this topic also will get shuffled a little bit, so it doesn't matter. Yeah. So this slide shows the references. I believe that the people who are undergoing currently in any of these courses will would have read this book, and I have just listed here to just to give you the perspective of what are the topics we are going to take from each of these references. So mostly I have not moved out of this references. Most of the content I am following only these references. So we will now just begin our lecture. So what you are seeing here is a very nice image, but which is clearly depicting the spectacular failures. One of the spectacular failures, what you see is a ship is vertically getting split into two, and this is an oil tanker that fractured in a brittle manner by crack propagation around its girth. Okay, so I'll show few more images and then we will discuss why we are looking at this. This picture all of you must be familiar with. This is a pre-World War II above portion of the Titanic ship. This is a remaining of the Titanic ship on the ocean bed. Okay, and this is again a fractured tanker which failed somewhere around 1941. This again happened around World War II. The problem diagnosed that time are different nature, but some of the primary cause for this kind of failure was the usage of wrong type of steel. Basically, the steel with ductile to brittle transition temperature, okay, which is not a characteristic. So that is something called, people learned out of these kind of failures about design strategy, stay above the DPDT. That is, we will see all these concepts. I am just showing these images because why this subject? Why do we need to study this mechanical behavior of materials? So some of the spectacular failures we learned from these kind of big failures and then try to understand materials behavior. Okay, so some of these failures which I have shown here before, one of the primary reason people recorded in the literature is the riveted points, all they popped off during this accident. Mm. And all these rivets were made out of some material, iron-based material. Those days, probably cast iron and so on. So they had some, metallurgical property which was not characterized or which was not understood those times. Okay, so from that point of time, people started looking at very closely how these kind of failure would have occurred. Okay, so that is how we learn from this failures, right? So we will see one by one how. So other example is it is not just the huge structures, but also the other type of failures, right? So for example, these kind of oil tankers, they are also subjected to cyclic loading from the ocean waves. And what you are seeing here is a computer chip. Of course, they are subjected to cyclic loading. Here it is a thermal cyclic loading. And this particular image shows the hip implant, and which also undergoes cyclic loading, mechanical cyclic loading while walking. Okay, so this also one of the some of the classical examples of mechanical failure. You see that a big pipe which is completely broken. So this is characterized as ductile failure, and this is just a one piece, and it is considered as a large deformation. Okay, and the similar pipe which has been shattered into small pieces, characterized as brittle failure, many pieces, small deformation. Okay, okay, so you have different type of failures, and so now we will come to the main idea. Why do we study this subject? So designers of machines, vehicles and structures must achieve acceptable levels of performance and economy, while at the same time striving to guarantee that the item is both safe and durable. The important aspect is these 4 points. Designers have the challenge of keeping all these 4 parameters in mind before recommending any design, for example, right? You may have a design which is very good, sophisticated, but if it is not affordable, then it is a problem, right? And you may have very sophisticated design, but if it is not lasting for a long time, then also it is a challenge, right? So so designers have to think about all aspects, and then they need these materials properties in their hand, or at least the knowledge about the materials in their hand before they recommend any materials for their design, right? So to assure performance, safety and durability, it is necessary to avoid excess deformation like bending, twisting and stretching of machines, vehicle and structure. Okay. So slowly we are getting into what property we are referring to, right? So first we are introducing excess deformation, right? Like load bearing ability. Okay, any structure if you underuse should not undergo deformation, any excess deformation. Okay, like you should not bend or twist or stretch any structural materials, right? So that is important. In addition, cracking in components must be avoided entirely are strictly limited so that it does not progress to the point of complete fracture. So we are introducing another word, fracture now. The previous point is talking about deformation. Now we are talking about fracture. Some of the failures we have just gone through before, it's all fractures, right? Failures, major failures. We have seen spectacular failures, right? So it is better, to avoid the cracks in the components entirely or strictly limited. What do you mean by strictly limited? So some of the flaw may be there in the component. If the flaw size is too small, then also the material will sustain for some time till the crack grows into critical size. So that is what it means, strictly limited. Okay. Later we will see in the while we study the fracture mechanics, we talk about damage tolerance approach, right? If you have a component which contains even a small flaw, still it sustains the services, then that is called damage tolerance, right? So we have to think about this. A material can withstand a critical crack size, which will not cause the catastrophic failures like what we have seen before. Yeah. So what are the basic concerns? Right? The most basic concern in design to avoid structural failure is that the stress in the component must not exceed strength of the material. So the applied stress in a component must not exceed strength of a material. So this is intuitively, everybody understands, right? Even in day-to-day life, everybody knows that, even if you take a carry bag to go for shopping, they know how much you can put inside that bag, right? So if you overload the bag, you know what will happen, right? So intuitively, we may know all this, we may be practicing it in a day-to-day life. Okay, the same thing has to be applied in a engineering design as well, right? The stress, any component you take, any structural component, moving component, okay, you take a bus, you take a train, or you take a bicycle, anything moving, or any structural membrane, or any structural entity which is under use in an engineering setting or even a domestic setting. This is a very common idea, right? But we also have some other additional complexities. Causes of failure often requires further analysis. That is, the stresses are often present that act in more than one direction. Okay, that is, the state of stress is biaxial and triaxial. So it becomes a little more technical now, right? So we were talking about a very general, load or stress and strength and so on. Now we are talking about the direction of the stress, right? It could be a biaxial or triaxial. It could be more than one direction. The stress is coming from more than one direction, right? It's not necessarily unidirectional, or it could be biaxial or triaxial. That could be a more challenging than the one which the stress in a single direction, right? So that things become more complex. Okay. So the real component may contain flaws or even cracks that must be specifically considered. Okay. So any component may have the kind of flaws and cracks, right? So just before I mentioned the damage tolerance approach, whether the component or the structure can work with this flaw, whether it is the flaw exists in below critical size, that is the question, right? Or the stresses may be applied for a long periods of time. So there are some structures or components which are subjected to very long time, right? So then also you have to be cautious, because you don't know how the crack is growing or a flaw is growing as a function of time. That is why in most of the industries, people have the periodic check, right? Once in a while they inspect all the components. You also might have seen in an aircraft, when it lands, immediately you will see that engineers will go, once the engines are coming to a standstill, you would have seen that they would have, for every ride, the moment the flight lands, they go and look at the blades with a torchlight, very careful. They'll see whether any damage has occurred because of any bird hit or particle hit or something like that, any crack visibly observable, right, visibly noticed. Okay, so this is periodically done. So in this case, it is quite frequent, like every flight, wherever it lands and takes off, that examination is mandatory, because if something happens, it will be too costly. But like that, every machinery and every structural items in engineering setting will also be subjected to periodic checkup for the flaws, right? And finally, the stresses may be repeated, applied and removed, or the direction of the stress repeatedly reversed. So this is something come into cyclic loading, right? The similar pattern of loading, right? Like the tides in the ocean, the similar loading, right? Like your thermal cycling in a computer chip, just we have seen, right? Or the bio implants subjected to mechanical loading while we walk. They are all periodic, but repeated. Same type of stresses are repeated for a long time, continuously, right? And sometimes the stresses are also get reversed in direction, right? Not necessarily in same direction. A reverse direction also will cause some kind of a damage. We will see how these things are affecting the material behavior. So this these are all some of the points which addresses why we study this subject, right? As an engineer, how one can exploit this knowledge in designing any vehicles and structures and machines and so on.